Telecommunications, China. I'm very pleased to have this opportunity to share some of our research work with you. Thanks to the conference committee for giving me this opportunity. All right, now let's start. The title of my talk is Research on Tire Pattern Image Classification. Firstly, a brief introduction of myself. I'm the director of Center for Image and Information Processing, Xi'an University of Posts and Telecommunications, China. I obtained my PhD from Monash University, Australia, my master degree from National University of Singapore, my bachelor degree from Xi'an University, China. Alright, in case you complain that there are no pictures of the presenter, here you are. This is a picture taken in late of this September, quite a recent one, right? Myself with my postgraduate students, some of them, we have more actually. This picture, myself with some of my research team members. They are all staff in our university. You can find me easily, right? Okay. Now let's start with the four following parts. I will share with you our work done in tire pattern image classification. Firstly, background of the research. According to the data from the Traffic Administration Bureau of the Ministry of Public Security, China had nearly 400 million motor vehicles by the end of last year. Here are statistics about traffic accidents and the loss of life cost, injuries, and property loss. Similarly, in Pakistan, with the increasing number of vehicles available, there are more traffic accidents, which cause loss of precious lives and damage of personal property, etc. While in traffic accident management and solving of relevant criminal cases, tire patterns provide important clues to help the police in tracing the suspected vehicles. Nowadays, tire pattern analysis in practical scenario is mainly implemented manually. Hence, there is an urgent need to design efficient and automatic or semi-automatic tire pattern recognition systems. Such systems rely on image classification techniques. Alright, we can see that the research on tire pattern image classification, in short TPIC, is of great value not only because of the practical needs, but also in terms of theoretical research on fine-grained image classification. Fine-grained because tire pattern images are fine-grained images. Okay. Our research center was established in the year 2011. And we have a joint lab with the Public Security Department of Shanxi Province. The team focused on image and video processing with applications in public security field. The picture on the left includes most of our team members. The picture on the right includes some of our team members and some police staff in the joint lab. The police staff actually provide us useful information in application domain and also help us in obtaining useful testing data. Alright, second part, I will introduce you the self-built dataset. The dataset CIIP TPID. CIIP is a research center, and TPID refers to tire pattern image data. This dataset includes over 11,000 images, and it has not only tire surface patterns but also tire indentation marks. The collection of such data is not easy. It took us over 4 years to build this dataset with the effort of our postgraduate students. The tire indentation marks are on different carriers such as soil, sand, mud, etc. This is the largest tire pattern image dataset available for academic use, and it has been used by many domestic and foreign research teams. In addition, this dataset has been selected as a testing dataset at Multimedia Grand Challenge in international conferences, including ACM Multimedia Asia, ICME 2021, BCIP 2022. These are pictures taken on the spot at the Grand Challenge. The first one, myself hosting the Grand Challenge at ACM Multimedia Asia. This is a conference mainly with participants from Asia in multimedia processing domain. The second picture, myself with our technical staff organizing the online session at ICME 2021. The third picture shows the presentation from the first winner. The picture at the bottom include the winners, winning teams. The guy in the middle is the first prize winner, the team leader of the first prize winning team. Okay. Now the third part, I will share with you some of our research done in tire pattern image classification. We have to admit that there is limited amount of work done in this field because there are a fewer number of researchers in this area, and there is a lack of standard data set. Our data set is open to the public in the year 2019. It was open to the public in that year. The development of techniques in TPIC mainly has these 3 stages. In early stage, researchers focus on extracting low-level text features from tire pattern images. The obtained features were then sent into image classifiers such as support vector machine for classification purpose. More recently, convolutional neural networks were used to enhance the performance. Well, a potential future research trend is few-shot learning. We will explain this later. Alright, firstly, a text feature descriptor we proposed named HawkDG. Hawk is referring to histogram of oriented gradient. DG means dominant gradient. HawkDG is found to be robust not only to illumination and scale changes, but also its rotation environment. Experimental results prove the effectiveness of HawkDG. It provides performance close to that of CNN, and it performs other traditional text features. Let's see Hawk descriptor. Firstly, the magnitude and direction of gradient are extracted from each pixel in the image. To construct Hawk descriptor, the entire image is divided into cells of size 8 by 8. From each cell, a feature vector of length 9 is obtained. We won't go to the details of the calculation, as you can find that easily. the global feature vector, we observed that there is a dominant gradient here, which is the dominant component with maximum gradient magnitude. Dominant gradient is robust to rotation, illumination, and scale changes. Using this dominant gradient, we can align the cell feature vectors. These are tile pattern images with different shooting angles. Red arrows show the dominant gradient we obtained. Using these equations we designed, we can align all the cell feature vectors based on the dominant gradient. In this way, the feature vector obtained will be rotation invariant. Alright. We normalize the aligned cell feature vector and then concatenate the vector from all the cells to get the final HawkDG feature. Alright. Okay, again, SVM classifier is used for classification purpose. In our experiments, we compare the performance of the proposed HawkDG with Hawk and other traditional text features as well as CNN. It is observed that HawkDG provides performance as close as that of CNN, and it outperforms other traditional text features. It is quite amazing that in such case, the performance of HawkDG is nearly slightly higher than CNN. This doesn't mean that HawkDG is always better than CNN for other tasks as well. But it shows that HawkDG is quite an efficient descriptor for tile pattern images. Alright, in summary, by defining circular cells, which is used to align the cell vector features, the HawkDG feature is made to be robust to rotation environment, to rotation changes. Yeah, because we designed a way to align each cell feature vector based on the dominant direction. Okay. Next, we have proposed a way to perform tile pattern image classification based on transfer learning. We know that tile pattern images are not easy to collect, and there are not large amount of samples available. Hence, we make use of the transfer learning concept here. Firstly, a pre-trained model using large image datasets such as ImageNet is obtained, and then it is fine-tuned using tile pattern images to obtain a new model. With this new model, we combine image feature from different fully connected layers to form the final tile pattern image feature. Then, using this feature for SVM classification. Experimental results prove the effectiveness of the proposed method. The framework of the method. Firstly, a pre-trained model, and then fine-tuned based on transfer learning, a new CNN model obtained, different layers features from different layers are combined. And then PCA is conducted for dimension reduction. Thus, we obtain the so-called transfer learning feature, TLF, which is sent to SVM classifier. All right. Tested on type pattern image dataset, we find that TLF, the proposed method, is effective compared with other text features. We also compare the way of using multiple layers features, combining different layers, compared with using single layers only. Surely it is proved that fusing features from different layers, we can get better performance in terms of classification accuracy. Right. In summary, transfer learning fine-tuning is a useful way for image classification with limited amount of sample data. All right. Okay, next, few-shot learning. We know that deep learning, convolutional neural network, the outstanding performance of CNN relies on a large amount of training data. When we have not enough training data available, there will be a overfitting problem. Few-shot learning is designed for deep learning with small amount of training data. Okay. Graph convolutional neural network, GCN, is a type of few-shot learning technique. Based on GCN, we propose an improved version. This method we proposed use cross-attention mechanism to select salient region features. That is, important features of the original image are extracted, which is used as the initial node feature of the graph. In this way, we enhance the performance of the graph convolutional network. Experimental results prove the performance of the proposed method, which is effective. All right. The proposed method is named in short as GCN-NFO. GCN refers to graph convolutional network, NFO as node feature optimization. The method contains 3 modules: embedding module, cross-attention module, graph convolutional module. In the embedding module, the initial feature is obtained using some convolutional blocks. In the cross-attention module, the important image feature are obtained or extracted from the support set and the query set. We will not go to the details of the equations here. Anyway, step 2, this module will obtain important features, which is used in step 3 as the initial node feature of the graph. All right. Okay. The graph itself iteratively will spread or adjust the structure itself. And in this way, by optimizing the initial node feature, we enhance the performance of the graph. All right. The proposed method is tested over different data sets with different contents. With supervised learning tasks over different data sets. Also with semi-supervised learning tasks. All these results proves the effectiveness of the proposed method. Alright. In summary, using cross-attention mechanism to obtain the more silent features. In this way, we optimize the initial node feature of the graph. Yeah. By optimizing the initial node feature of the graph structure itself has a so-called message passing mechanism. In this way, the performance of GCN can be enhanced for few-shot image classification task. Alright. Just now we have explained some of our work done in tire pattern image classification, including texture feature descriptor we proposed, including transfer learning based texture tire pattern image classification and few-shot learning. Now let's come to the last part, conclusion. In conclusion, we can see that tire pattern image classification is important as it can provide useful clues for police in traffic accident management and relevant case solving. And in this talk, I have shared some of our research work done in this field. Surely in our research team, we have researched not only on tire pattern but other types of images and videos, and other image video analysis tasks such as event detection, scenario construction, as well as video retrieval. Alright, if you are interested in any of these topics, you're always welcome to contact us. Okay, now here for future contact, here I provide our email address for you. And you're really welcome to visit us in Xi'an. Sorry.